super excited to present this really cool research project, pun intended. We're fortunate to receive funding from the Canadian Mortgage and Housing Corporation here in Canada, and I'll give a proper acknowledgement to them at the end. So topic, cold air distribution, which some of you, particularly the mechanically minded, may have come across. We've been exploring this as an approach to meeting passive house cooling loads. So a little bit of background on kind of the motive for the project. So we see, passive house has been applied in numerous projects, numerous multifamily projects. And with the drive to electrify buildings, what we're seeing is separate systems that all come with a particular cost, right? We have our separate ventilation system. We have an air source heat pump, typically. Could be geothermal sometimes, but that's typically providing heating and cooling. And then often we'll have a separate heat pump for domestic hot water, right? So 3 different systems, again, all with their price tag. And often we're still seeing projects not go full electrification because of capital cost. And one of the key barriers is that no system has really been designed for the commercially available, I should say, that are for the small loads in individual apartments of multifamily buildings, right? And so what we end up with is what I can call a conventional high performance mechanical system, but this kind of promise of reduced, simplified mechanical systems, reduced costs that we saw in the early days of passive house hasn't really been realized, particularly in multifamily projects. And one of the key challenges here is, well, we know from, there's been examples in Europe and even some in North America that actually in a passive house, you could deliver all of your heating through ventilation, the ventilation system, right? Now, this is the only math I'm going to show in the entire presentation, but we are in the construction tech session, so we're allowed to get a bit nerdy here. So some of you from, have done the passive house certified passive house designer training might recognize a formula, this formula here. I've tried to convert where I can, data between metric and imperial. Not done that exhaustively, but anyways, there's the opportunity to heat through the ventilation air. Generally not done, right? And part of the reason is because, well, we can't do that with cooling, right? So if we apply the same formula to the cooling case, essentially we have a much lower capacity of the ventilation air to deliver cooling. And a key reason is because the delta T from room temperature to what our supply delivery temperature is, it's just smaller in the cooling mode than in the heating mode, right? And so get a smaller capacity, can't meet our loads. Well, there have been, I've seen a couple systems actually on the market, not on the market, rather they're actually in China, that have been developed to overcome this by essentially increasing the supplier. So taking the ventilation air, tagging along some recirculated supply air to boost the airflow and the capacity of the cooling of the unit, right? Well, these aren't available in market. There's no, in the foreseeable future, anything like this that's going to be on the market as far as I'm aware. Please correct me if I'm wrong. We're always interested in seeing what other new products going on the market. But if we increase that delta T for cooling, plus if we're dealing with multifamily buildings where actually the amount of air that we're delivering, let's say per square foot, is actually higher. There's higher occupant density, so we generally need more air per square foot. Those 2 elements combined can actually increase our cooling capacity, potentially closer to our heating capacity. And depending on the climate, this may actually be sufficient for meeting our cooling loads in a passive house. So this idea of supercooling the supply air is actually nothing new per se. It's been done in conventional, so non-passive house, commercial and industrial buildings. It's known as cold air distribution, and actually ASHRAE has a design guide they published in the 1990s on cold air distribution. So it's a well-established strategy, right? And even according to ASHRAE, it's a strategy that can lower mechanical costs and reduce energy consumption. So this is a proven strategy outside of residential sector. Um, so what we're going to do here is say, oh, well, can we apply it to residential, right? So essentially, we're going to take our ventilation system, provide our fresh air, we're going to heat it, and we're going to supercool that air. And if we combine this with an air-to-water heat pump and to basically switch to a hydronic-based system, we could actually potentially use one single air-to-water heat pump to deliver our heat, to generate our heating, cooling, and domestic hot water. So that's the goal, and you can see we'll end up with a reduced number of pieces of equipment, right? And ideally, this brings down the capital costs as well as potentially simplifies the maintenance. Okay. Now, the challenge with cold air distribution is the supplier delivery temperature, right? So we're targeting a 41 degrees Fahrenheit supplier temperature coming into the room, where you can imagine, that might be a challenging thing to do. And indeed, there are three key risks that this introduces. First is occupant comfort. So, if we're not getting good air mixing, we could get some air dumping, cold drafts. So how do we deliver the supply air into the room without causing occupant discomfort? Condensation, well, that air temperature of the spire is noticeably below the dew point in the room, right? And so how do we ensure that condensation won't form on the diffuser? And then mold growth. If air is blowing around, say, the drywall surrounding our diffuser, how do we ensure that both that surface as well as the diffuser itself remains warm enough to mitigate mold growth? So these are the three key questions and technical challenges that we investigated in this first phase of research. So essentially, what we did, we actually rented some space at the university laboratory. They had a rooftop test facility that had two test chambers. And we essentially went around creating an experimental setup in each of these test chambers to see if we could validate cold air distribution in a residential setting, right? So just a little bit on the experimental setup. I could spend hours talking about the experiment and the setup and all the challenges that came up, but time does not allow me to do that. So just a little insight. So we built basically a small partial suite bedroom, kind of a mock bedroom within each test chamber. They're about close to 50 square feet. So, too small to really be considered a bedroom, but that's all the space we had really to work with within each test chamber. Created a SketchUp model to plan out the actual construction of the setup, right? And then I prefabricated, so, you get a nice follow on from our, the Reimagined Buildings prefab session, because even here I was doing some prefab, in this case in my basement, but basically prefabricating the wall and ceiling panels, basically so it could fit through the chamber door, because they wouldn't fit if they were fully constructed. So, you can see even upfront design, even in experimental lab work, pays off because it actually all fit nicely together without any challenges from the construction point of view. So that was nice to see. In terms of the overview of the test chamber, you can see here we've got what I've labeled West and East test chambers, and they have their own separate heating, cooling system attached. So it's basically a recirculating fan coil unit. It's connected to a chiller and like a boiler, and there's also an attached HRV as well to that. So basically, we use the systems in the lab to basically recirculate our cooled air into each chamber. Okay, so some of the things we looked at to measure in the experiment was naturally we're providing cold supply air, so we wanted to measure, okay, what's the temperature, relative humidity, flow rate, and speed. at the diffuser. We did some thermographic imaging to determine the surface temperature of any of the surfaces that we were interested in or saw could be at risk. We also had a thermal comfort station. So this is something we actually borrowed from the University of Toronto because these are really expensive pieces of equipment. So fortunately, they had one we could borrow, and we were measuring basically things like temperature, relative humidity, room, air speed at different heights, basically according to the ISO 773 standard, as well as mean radiant temperature, which is an average of all the surface temperatures in the room, essentially. So that helped us assess comfort. And then we even measured temperature stratification through IR imaging, basically using toilet paper streams, a very high-tech solution to see the temperature distribution. Okay. And in terms of the actual experimental procedure, we were targeting, again, 41F supplier temperature coming out of the diffuser. We looked at 3 different flow rates, 14 CFM, 35 CFM, and then between 53 and 71 CFM. And we also looked at the airspeed ranging from about 200 to 1,000 feet per minute. And different diffuser positions. So looked at wall mounted, about 8 inches below the ceiling. So anyone who's familiar with the Coanda effect, right? That kind of induction along the ceiling. We tried to take advantage of that, as well as another reference of a ceiling mounted position for the diffusers to see as a reference. We tried a bunch of different diffuser types from proprietary diffusers and materials, one made of pure insulation. We also tried this anti-condensation paint that a colleague informed me about, as well as for comparison or reference to conventional diffusers as well. Basically diffusers you could pick up at local hardware store. And then, first time doing it, and certainly I was a bit naive going into this isn't the typical stuff we work on day to day, this intense lab work. So we were adjusting the protocol based on, in real time, basically based on results, as well as discussion with colleagues. So again, I could spend many an hour speaking about the whole experimental experience, but I'll highlight a couple key things that are really impact practical implementation of this solution. So one of the initial things I struggled with was I saw a major temperature increase from the coil, measuring the temperature off the coil to at the diffuser, seeing about a 14F temperature increase. And that was in like I don't know, maybe 8-10 foot section of duct, right? Not very long duct, thinking, oh, direct into the room. So I'm like, okay, well, very small amount of insulation on the duct. Let's super insulate it. So I was basically built a shield wall of mineral wool around the ducts, the fan coil unit, and so on. But that wasn't doing anything. And basically it was because there was just too much surface area. These are honking ducts for the amounts of airflow we were dealing with or trying out. So in the end, I resulted in painstakingly building an insulated a duct of insulation within the existing duct, which gave me about a 5-inch equivalent diameter, as well as insulating all around the cooling coil and fan coil unit. Yeah, that took a very long time, but in the end it worked because towards the end of the experiments, we actually managed to achieve under 36 F at the diffuser. So actually below what we were targeting, which is pretty amazing. So really stress tested the setup. And now another practical challenge we had, which will inform the implementation in actual buildings, is despite decent amount of care, wrapping double layer of insulation around the ducts, we see thermal bridging. I mean, it shows up. If there's a weakness with these kind of conditions, condensation is gonna show up with such cold air in the duct. So that became readily apparent. Okay, so let's look at some of the results that we actually achieved. So one of the early challenges or early things we saw was air leakage, and that became quite apparent on the thermal images. You can see nice images just showing that cold air wherever there's a little crack or leak or something in the particularly around the diffuser. Um, then we see the cold air. And so really it's about sealing, seal some more. I mean, we know this from, the envelope side of things. Just got to do a really good job sealing, right? And as you can see before and then after the sealing, huge difference, right? Basically, you're not seeing any air leakage, pretty much no, yeah, I don't think there's any air leakage here. It was challenging having to air seal the diffuser to the duct in the wall. That took some that took some time, and I was testing quite a few diffusers, so swapping the diffusers out was quite time consuming. So I ended up coming up with a bit of a kind of modification to the setup to make it easier to swap diffusers. Um, but yeah, I mean the air leakage, not just in the diffuser, leaky plenum boxes, right? It just shows up wherever you have leaks. And this is an insulated plenum box. They've insulated all the interior surface, right? So this isn't really conduction. This is really air leakage. So in terms of the diffusers, so we have I think was it maybe 10, 11 types of diffusers we tested out. All sorts of interesting on. We were liaising with a bunch of manufacturers to see which ones might be a fit. Understand, some of them were claiming like, hey, you can use this with cold air. So we wanted to dig deeper and then ultimately just test them to see how they perform. Now, none of these, like, I don't think any of them were really um, the manufacturer wasn't claiming, as far as I can recall, hey, we're going to work with 41F supply air, but in conversation they're like, yeah, it should work. Uh, so there's different proprietary materials. Some I don't actually know exactly what they're made of. Some I think maybe plastic material. We have fabric diffuser, right, which is used in like schools and industrial settings. Um, and I mentioned we tried this anti-condensation paint as well. Kind of in brief, the majority of the diffusers failed, whether they were made of metal or proprietary material. Um, Most of them had condensation on them. Some of them didn't have condensation, visible condensation, but when I touched them with my finger, I could feel moisture. So moisture seemed to be accumulating, even though it didn't turn into condensation. So condensation maybe is not a concern in that case, but moisture accumulating maybe over the longer term could lead to mold growth, depending on the substrate. Does mold consider that a good viable medium? So that would require separate ongoing testing, which was beyond the scope of our study here. Yeah, I'm really the main diffuser that worked was the one made of insulation, which is surprising, not surprising. But yeah, so that's an interesting. I mean, we kind of expected that, but good to see that. One particularly interesting thing we tried to mention this anti-condensation paint that a colleague got me onto. So we tried this. So we took this. This is one of these proprietary diffusers, and I set up the diffuser with three different situations. Basically, in the middle we have no paint on there, no anti-condensation paint. On the left, I have one coat, and then on the right, it's three coats. Kind of manufacturer recommended three coats. I didn't take actual measurements of thickness. Didn't have one of those thickness gauges on me at the time, so I don't know exactly how thick I got. But you can see this difference, right? Here, clear condensation in the middle with no coating. With one coat, there's no condensation, but the finger touch, I could see it feel moisture on it. On the right side with three coats, dry to the touch, which is pretty incredible. So this magic paint, you think it's one of these crazy claims, right? An anti-condensation paint, but it actually worked. And just for reference, there is XPS. I put behind the diffuser the XPS behind here. So this is actually airflow. It's not due to conduction through the diffuser. Another lesson, if you will, is anything within that airflow that could obstruct it or slow it down is going to form condensation on it. So you can see this tape, little bit of innocent tape that, expanded, or, just how I ended up taping it. It was covering some of the hole that condensed. The sensor wire had condensation on it, right? This fabric material, which actually didn't have any condensation, but was moist to the touch. So no condensation, but the metal framing that was supporting it, part of that happened to be exposed, and boom, we got condensation, right? The exception to this condensation rule is insulation. So if you put insulation in front of the airflow, it doesn't condense. Because one of the things I was doing was trying to adjust the airflow through the diffusers, so I had to block them off in a way. And so in the end, I couldn't tape them or block them other ways besides just basically putting insulation in front of them. So here's just little balls of insulation I was squeezing into the holes to control the airflow. In terms of surface temperature, right, another risk here. If we look at around the diffuser, right? So not on the diffuser, but around the, so let, I mean, it's drywall around the diffuser. So what's the temperature around the diffuser? Well, we found that basically any diffuser that is sending air parallel to that surface that it's installed, the diffuser is installed on, right? So radially outwards, essentially, we see low temperatures. Not really that surprising, but this is a nice reference to have, right? So you can see here, so I didn't convert all of these to Fahrenheit, but we're at, close, just above or just kind of below the mold growth, the risk of the point of risk of mold growth. So we don't really want to be hovering around that. I think we want to be, well above that. I mean, there's only so much accuracy you can get in these lab setups. So I'd say this, would be danger territory. And even one here at, the air was kind of projected 45 at a 45-degree angle. It wasn't 100% clear if this was air or air leakage. Didn't have enough time to kind of really investigate further, but certainly a questionable result there. If, on the other hand, we project the air perpendicular to the surface, so for instance, on the wall, projecting it like the Coanda effect just below the ceiling, around the diffuser here, we didn't have any issues, right? So, you can see both thermographically and also I've got temperature spots here well above our risk of mold growth. So provided we seal up the diffusers well, we project the air horizontally, it works well, right? We even did a reference of floor. This is very typical, at least in Canada, of having floor-mounted diffusers, air pop, pushing out from above. And certainly at the cold air temperature, that was problematic. So generally not recommended anyways. But yeah, this certainly wouldn't work with cold air distribution. So essentially, what we found is, if you're projecting it using the Coanda effect, it works well. So we have it both around the diffuser and also if we look in the airflow path, right? So along the ceiling, you can see here 24 degrees C. So what is that, 78 or something Fahrenheit? Really high. So this is 5-degree air about coming out of the diffuser and right into the ceiling right above it, where, I mean, barely any difference from the room temperature, which is pretty incredible. So as long as we don't have air leakage around the diffuser coming out in areas of the diffuser we don't want it coming out of, this is actually a good strategy. We even tested a conventional metal diffuser. Again, you buy at your local hardware store, and the Coanda effect works with that. So you don't technically need a specially manufactured diffuser with special slots or whatever that are going to, project the air. It actually works with a conventional diffuser. Right. I wouldn't use this because it'll condense on the diffuser, but in terms of airflow, that was very interesting to see. Right. We even did a smoke test. So I filled the fan coil unit with a whole bunch of smoke. and had it inject air through. And so this is again cold air, your 41F air coming out. And look at that. It's actually, super thick coming out, but mixing beautifully in the room. Right. And the only challenge we had, well, I'll come on to that actually later on. But yeah, so clear another visual showing good mixing of air. In terms of comfort, so I mentioned we have a thermal comfort station. Normally, uh, to simplify the experiment, that comfort station is kept in one position, typically in the middle of the room, and then you do all your experiments with that station stationary. Essentially, you're not moving around. Well, as we were getting results, in discussing with the mechanical engineer who was supporting us on the project, uh, they were concerned, oh, could there be temperature distribution around the room? So we're like, okay, well, for these final experiments, we will move the station around the room to see if there's any impact on location. Okay. Here's a very brief summary of just a couple of the diffusers we tested. What we found was really the wall-mounted solution was really the only one that could ensure occupant comfort. Ceiling-mounted did lead to some dumping of air. So here's an example where we have a ceiling-mounted diffuser, different positions. These are just three of the positions of the was it five positions we looked at. Um, but just kind of trying to show things in brief here. You can see in this case, one of the locations by the diffuser wall was basically uh, quite a low comfort rating, whereas the two these wall mounted showed, for example, one of the proprietary material diffusers, and then also one of these conventional metal diffusers. Both actually had really good comfort results. They slipped into category B occasionally, but that was just slipping out of the category A. So overall, really good result there. Uh, uh, Temperature stratification in the room was also really good. So typically we're in a passive house, we'd see about a 4F between the floor and the ceiling, and that's pretty much what we got in the room as well. So despite, super cold air coming out here, we still get good or low amount of stratification. And then also supply airspeed. This is not something that we had originally planned to measure, but just as the experiment went on, I realized actually this is something I should track because this may be important for actual diffuser design in different rooms. So I started to track it later on in the experiment and found that basically in general, there's no comfort difference. The difference in comfort or in low surface temperature risk with airspeed, whether it was a lower or higher airspeed. The one exception is if you have a very high airspeed in a small room, then what can happen is that air can actually hit the back wall, which is was doing in the room and dropping down that wall and then creating a draft and showing up as a noticeable difference in the room velocity. So here measurements of room velocity at a medium rate and then quite a high rate. And we saw a fairly large uh, difference in the airspeed. So just a little summary here. So the three risks we look at: occupant comfort. Well, we've confirmed that using the Coanda effect, we can ensure occupant comfort even at these really cold delivery temperatures. We do want to make sure we match the airspeed range that we might see coming out of the diffuser to the room size. Right. Mold growth, with the right diffuser selection and positioning, that is a risk we can mitigate, in particular dealing with air leakage around the diffuser. And then condensation, provided we choose the right kind of diffuser, install it correctly, and also install ducting correctly, then we can mitigate that. And I'll come back onto the ducting side of things in a bit. Okay, so overall success for our the factors we investigated. In terms of some recommendations for implementation, ducts naturally when you want to fully air and vapor seal, it's critical to avoiding condensation. Recommendations, 50 mil or 2 inches of insulation mineral wool equivalent. You could consider actually using ducts that are made of insulation, not insulating, metal ducts or other types of ducts. And in terms of making sure we don't get a big temperature gain between the coil and the diffuser, we want to right size optimize really the diameter of the duct and really try to reduce the length as much as possible so we get less heat gain. The diffuser itself, ideally it's made of insulation, food grade. We used XPS just as a test, but we wouldn't want to use that in a duct, an actual ducting carrying ventilation air. Mentioned the Coanda effect really works well. So the wall-mounted diffusers, 8 inches below the ceiling. Target airspeed about 200 to 600 feet per minute. Could go a bit higher if it's a larger room. We do want to watch the noise. That's something we could check in it was a noisy lab. Something we might investigate in future is in terms of noise output from these diffusers. And then anti-condensation paint that's showing some promise, surprisingly. We got to apply it appropriately. Probably the factory apply would be ideal, and I'm gonna make sure it doesn't get damaged. It could get scraped off. So that would be a concern as well. Okay, so moving on to implementation. So that was our first phase of research. We're fortunate to receive funding to actually implement the solution in a few projects. So we've actually got 6 projects across Canada, literally coast to coast from Victoria, BC to Pictou, Nova Scotia, and from small 3 units up to a 42-unit building. We've got one retrofit, different markets of affordable housing, using one for urban Indigenous community, and mostly rental, but there's also a condo structure as well for one of them. So great diversity. So and 4 different provinces, variety of different climate zones. So really testing the universality of this solution, at least within Canada. It's a question of how far can we go south with cooling loads. That's not something we've really looked at, but certainly there'd be places in the US that this could be applicable to. As part of this, we're going to be doing extensive post-occupancy evaluation, including 2 years of technical monitoring, occupant assessment and engagement to make sure they're comfortable with the system as well. And unfortunately, we have all the project mechanical engineers on board to implement the solution. That's not always easy to get their approval when you're trying something very innovative like this. And then, we've got a great collection of partners from our build partners actually willing to, implement the solution on their builds. Working with a couple manufacturers for support with their integrating their products. Because essentially what we're trying to do is take off-the-shelf, commercially available components as much as possible and basically combine them and operate them in a unique way. And we're going to be doing monitoring. So we've got some partners for monitoring as well as education partner to help us, develop educational materials for the solution, as well as organizations that are going to help us disseminate the results, and also housing providers who have said, well, we don't have a project that fits into your initial project, but keep us posted because we're keen. If it does work out, we'd be keen to implement the solution as well. One of the first things we're doing, because we've identified duct installation as a key challenge around condensation, we're investigating different strategies to mitigate that condensation, as well as that temperature rise from cooling coil to diffuser. So we're trying out different products and materials. EPP foam is one of them, which some of you may have come across with HRV casing. There's also prefabricated versus site-built. So ready-made ducts you're getting from the factory versus site-building ducts from sheets of insulation. I'm really looking at ease of it and effectiveness of the sealing, can it maintain the desired supplier temperature? And where we can, we're going to test out noise production diffuser and see if we can, if we need to mitigate that. Okay, so I think that's wrapping me up. Just in time, really, within that time window. So wanted to give a shout out to CMHC, Canadian Mortgage Housing Corporation, for their generous support of phase one. Sorry, what they've labeled it phase two. It was the first part of our research project. But it's phase two under their Building for the Future round, which is part of that broader housing supply challenge, which is really a program that's designed to remove barriers to housing supply in Canada. And then special thanks to individuals who really supported us through the research, Sheng Bozang from the University of Toronto, Wolfgang Hasper from PHI, and Kara Sloat from Hammerschlag and Juff. Yeah, and that's me done for the, I guess, formal presentation. So pause there, and I know there'll be questions ensuing, but I've forgotten who I'm supposed to hand it back over to now.
Thank you, Andrew. I'm sure we have some questions, but excellent presentation. Even better now, even though I did see it when we were in Austria for the conference. I enjoyed it then, and this version is great. Maybe the altitude has me thinking a little clearer headed or so. I'm not too sure, but I think before we get into questions, if we can shoot it over to Zach for the sponsors, that's I think where we're going, right? All right.
Thanks, Kevin, and thanks, Andrew. That was amazing. I want to just take a quick moment to thank the fine organizations that make our work at Passive House Accelerator possible. So a big thank you to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Thank you, too, to our founding sponsors, 475 High Performance Building Supply, Ingui Architecture, Glavel, Minotaur, Partel, Rockwell North America, Stocorp, and Zola Windows. And thanks too to our champion sponsors, Boizo, Gradient, Icon Windows and Doors, Intelligent Membranes, PH Air Seal, and Source 2050. And thanks to our patron sponsors, Brennan, Euroline Windows, Holstrom System, Inotech Windows and Doors, Lamelux, Longboard, RDH Building Science, and Sanderson Sustainable Design. Thank you, sponsors.
Amazing. Thank you, sponsors. Indeed, we cannot do all of this great work without them. So we are very appreciative, and equally appreciative, Andrew. Every time you present with us, you take me further out over my skis. And I really love it, because pushing that envelope literally to the interior this time and showing us why air sealing matters so much and how it results in comfort and health is everything, right? Because our clients don't care about performance and building science if they don't feel safe and healthy, and if they don't feel comfortable, because that's the hallmark for Passive House. So really appreciate all of the takeaways today, and I'll share a lot more comments in a minute, but it would be fun just to dive into a couple of questions first. So John S., you are up first if you'd like to unmute and share your question.
I wonder if you could talk about the, by the way, thank you, great presentation. I'd love to hear about condensation inside the ducts and what factors increase condensation along the inside of these tubes.
Okay, interesting. So the condensation within the duct isn't really an issue. I mean, I didn't crack open the ducts to see coming off the fan coil. Essentially, we fully insulated the interior of the duct from the fan coil to the diffuser, so I wouldn't have been able to see that anyways. There wouldn't have been anything. But it's not really inside the duct that's a concern. It's more the outside, because that's the side of the duct that's going to get cold. Whereas, the warm air from the room is going to hit the outside of the duct potentially and then condense. Inside, I mean, the relative humidity off the coil it's probably not 100%. I mean, I don't know, probably between 90 and 100%. I mean, the coil, just how air flows over a coil and whatnot, I don't think you get fully 100% relative humidity. But that air is only going to warm up as it goes. So it shouldn't really lead to condensation as it travels through the duct. It's more on the outside of the duct.
Fantastic. Thank you for that question, John. And Andrew, I am so curious about the biggest takeaway that you had with regard to the distribution, and that this vertical distribution, or excuse me, the wall-mounted solution is the one that really ensures that occupant comfort. And I'm just I don't know that I'm ever going to specify another delivery system now that I've seen this. So I really appreciate how practical you made it and how easy it is to put into our designs. Who do we have up next? We have Enrique. Hi, Enrique. How are you?
Hi, Sharon. Good, thank you. And thanks, Andrew. Great presentation, great research. I wonder if how does I mean this approach behave when you have very high external or exterior humidity, very high dew points. Did the system did some actual dehumidification there, or you didn't have to do that, or how did it work?
Yeah, it's interesting. I mean, then that gets into a bit of kind of the user interaction with the house and how does it affect if you open windows and bring in a bunch of humidity, is that going to put the system at risk or the solution at risk? So essentially, I actually early in the experimental work, I was using the equipment that was there, and the equipment's all oversized, so I couldn't actually regulate the interior conditions very well, and I was getting these big swings, and we were like stressing. We ended up stressing the interior conditions. We had 27 C, so it was like inside temperature, which is like 84, 85, and I'd have to do the calc, and high relative humidity, like above 60, which is, even more absolute humidity at that temperature. And for instance, that insulation diffuser there's no condensation on it at all, right? So as long as it's fully insulated and sealed properly, fluctuations in the indoor relative humidity shouldn't cause an issue. And actually, this solution is really good at dehumidifying. Maybe not in tropical climates or whatnot, but because we're having such a low supply air temperature, the amount of moisture in that air is much lower than conventional. So you're actually dehumidifying much more. And indeed, I was struggling at the high airflow rate. I was struggling to keep the humidity level high enough in the lab, in the room, the test chamber, because it was dehumidifying so well. I ended up having 2 portable humidifiers going basically to try and keep the relative humidity up, plus a space heater, to offset. So definitely, I mean, yeah, how far we can stretch it into what climate zones, I don't know yet, but it does do a great job at dehumidifying.
Okay, thank you.
Amazing, Andrew. I feel like you're the bartender of supercooling. Like you have this whole mixology, all these recipes, and they're delicious. So I think our next question up is from Brian. He's asked us to read it for him. And he wants to know, in making ducts out of insulation, did the surface texture of the insulation impact the airflow?
Great question. So in the lab, I actually first tested out using the 3-inch semi-rigid ducts that a few manufacturers thing. And the challenge was insulating those, and they ended up with more surface area. And so I switched to just a conventional metal ducting that I got from, again, local hardware store, and then just manually insulated it. That's not ideal for this solution, which is why we like the idea of ducts out of insulation. But yeah, they're kind of surface. Do they have a lot of friction? Is it a rough surface inside? I haven't actually looked at that in our initial testing. The EPP foam, interestingly, when it's manufactured, it actually has what they call a bit of a membrane, which is a kind of smoother surface coming out of the mold, which may help. But yeah, that's one of the things we're going to look at in the actual testing is what's the pressure drop through the duct network, because we want to optimize a smaller size for lower heat loss, but that increases the pressure loss. So that's why it's kind of a optimal, you know, and that might change project to project.
I hope that answered your question. And honestly, Andrew, did you also test like the duct delivery shape? Did you play with that at all, knowing that how these ducts get installed often can take some pretty violent twists and turns in these residences?
Well, I had enough variables in the lab to deal with that that was not something I was going to introduce into the
I
lab.
liked your variable where you connected and you showed the connection condensing. And I'm thinking the rigid insulation when you're making the ducts, you would potentially have more of those joints, right? So I like the move to the round, and the amount of variables was incredible in temperature and in flow. And it was really such a fantastic experiment. I know Mary James just recently wrote an article about this research project, and it just went live on the website. Kim is going to throw that link into the chat. So everyone, please have a look. It's, I think there's more to absorb here than we can do in 1 hour for sure.
Okay,
How long?
sorry.
Hi, Mary.
Hi, I just have to say it was Andrew who wrote the article.
Oh, fantastic. Well, I'm sure you were part of making that happen. So thanks for chiming in. And Andrew, I'm really also curious about how long the whole process took from like writing the grant, you know, application to dreaming this up and figuring out how to attack this problem, to creating this presentation, creating for you know, your Germany presentation live, and then again here with us. So basically, what does a timeline like this look like from a research perspective? And then what kind of team was involved?
Okay, yeah, timeline. I can preface this by saying I went way over budget. I was a bit naive in what this would take. But if I factor especially in the effort to get the grant, like I actually wrote applications for 2 grants. The first one wasn't successful. I repurposed it for the second grant, but there's still a lot of effort. So, you know, I don't know, 100 to 200 hours on grant writing to really properly conceive of this, to be able to write a grant and put a budget to it and all that. And then you know, we learned of receiving the grant in June of last year, and I knew right away we're gonna have to get going right away. So as soon as we got the contract signed, like July, it was go go go. Up until, and then so working with the University of Toronto, we could only have the lab for so many weeks. And so we ended up, I think the experiments finished. So from like sign a contract to, which is July, I can't remember the exact date, to end of October is when I think like we pulled everything out of the lab and could take a small breather. So it was probably the most intense I've worked in my life, evenings and weekends pretty much. So I thank my wife for the support during that time.
Yes, 100%. The PH spouses know very well when we get a hold of something like this, we aren't going to let go till we have our answers. And thank you to the spouses. I don't know if we have Sean St. Amour's question. What am I talking about? Sean,
Yeah,
are you here?
all good. I am. Great stuff, Andrew. And I think adding on to your intro from now on, we'll definitely use bartender of pH mixology. Shannon, that was a great line, and that was pretty remarkable. I just want to say it is remarkable, you know, in the 4 years of the accelerator and all of our live events, that we've gone from, you know, hair dryers for heating and a bag of ice and a fan for cooling to the level of in-depth knowledge we have here. And so this one's an easy kind of question Andrew is just, do you know at the Passive House Canada Conference in Victoria if we might be able to see this project that is underway and maybe be able to take a deeper dive into to a live project that's trying to implement this research?
That'd be great. Unfortunately not, it's not under construction yet.
Okay.
But we have agreements with the build partners to do open house during construction, so people will come. So, stay tuned. We'll be in touch. And anyone who wants to stay in direct communication with us, like you guys will, I'm sure, share my details. You can send me a note. We've got a list of people that we're gonna, basically a distribution list that we can keep people up to date on.
Yeah, I know, great stuff. I'd love to see what I mean. Now that you've done the lab, done the testing, and now I've got a very diverse implementation process with projects across Canada. I mean, it's great to see different climate zones that'll get tested and see where this goes. And again, great research, and thanks again, Andrew, for all the hard work. And now we kind of get an idea of what happened to you in the fall of last year. You were in the lab, so
Yeah, exactly.
glad that you're out here talking about this great research and very detailed stuff. So thank you very much. Appreciate it.
Thank you.
And I'll piggyback on Sean's comments. The teamwork and the aspect that you pulled together, a multi-international team to work on this and to support the project is amazing. And it speaks to your work of a great trainer and a networker to see that you were able to create those partnerships throughout Canada. I'm jealous, but keep up the great work. And I'm totally into figuring out how we execute in North America airtight multifamily ductwork. It's a necessity, I think. I don't know if we can solve it in the passive house world, but I love the innovations that are happening. I know on multifamily projects that I'm on every once in a while, I scratch my head and I say, that's an air ventilation duct. It's not sealed. The mastic isn't thick enough. I'm like, there's better ways of doing this. And it's an uphill challenge to change the construction culture. So I applaud your work and thank you very much for your time and your partnership.
Yeah, Andrew, one of the things that you shared was something I hadn't even thought of, was these moisture resistant paints, right? Every time I think of a paint or I think of a coating, I think, make sure it's vapor open, make sure it's vapor open. You're working with something that's the opposite on this. And I'm curious about those coatings, and also, did you use like an aero barrier or anything like that? I know some of the multifamily projects we have in the States, certain verifiers will demand that aero barrier or aero seal be used on the ductwork for the multifamily, because if there is a leak, they can't reach it or repair it sometimes. So they build that into the spec, right? So do you see a potential here for that kind of surface application as well, or?
Potentially, I mean, certainly in a lab, it's not really a suitable environment to bring in a technology like that. I mean, I was playing around with the ducts, moving them and things, right? So that wouldn't have been a practical solution for that. Certainly, I mean, just more generally, we like to specify that, aero seal and the like, because we've had so many issues with ventilation commissioning and getting airflows. So outside of the challenges with cooling the ventilation air, that's a whole separate topic almost. It's this is still a question mark, is how do we do this in this application? And frankly, there could be some good learnings to apply, not to cold air distribution by itself, but also just ventilation in general. So I think that'll be a nice side outcome, if you will, of this research.
Excellent. It looks like we just had John drop another question into the chat. John, do you want to come back on and ask your question?
Since heat rises, I'm wondering if you could comment or talk about the possibility of placing heating ducts near the floor and cooling ducts high on the wall, perhaps swapping the source and return duct function between summer and winter.
I guess that's a possibility. I think based on our results here, looking at the temperature stratification within the room, that was 4F, which is on target with what we expect with passive house. So I don't think there's a need to do that. I mean, if you go floor to floor, you can see higher stratification. So that's something. But I think in terms of an individual room on a given floor, just the ceiling, sorry, wall mounted near the ceiling, that gives good comfort all year round.
Thank you. And of course, cooling load in a passive house is much more important than the heating load. Probably
It
even
can be, yeah.
And that was like the jump off thought for this whole presentation was that difference between cooling and heating, and with a warming planet and all of those cooling agents that we're having to deal with, I think 100%. Andrew, do you have like a line of mentees that want you to mentor them at this point? I think Sean and Kevin and I are ready to get in line, but
Well, happy. I mean, we're like, I love spreading the gospel about this kind of stuff. This is a unique project. We've never engaged in this kind of research before, but I mean, anyone who, I mean, if anyone's interested in applying this on their project, it'd be outside of our research funding. But certainly we could look at, supporting somebody. We're even talking to some folks, we've got our set number of projects, but hey, you're doing a multifamily. Could we do one? Would you be interested in like one floor of your four-story building? So limit the risk in terms of the application, but give them an opportunity to apply it.
thank you. It looks like Hans has a question. Hi, Hans.
Hey, mine was pretty much along that way too. I totally missed the boat, and I think some of it already was answered by Andrew. Is like, why do we have such a high delta T? Because according to PHI, we usually don't introduce that cold air, correct? Is this just a North American specific strategy now?
I mean, it's ultimately just the physics of the air. Like, unless you've got a very small cooling load, and there have been the odd project that have done cooling through the ventilation air. We have a single family home we certified in Gimli, Manitoba, and they just used a simple coil connected to the ground, and it was kind of semi-passive. And for the owners, that was sufficient to take the edge off in summer. They were happy, right? That's not really a scalable solution necessarily, right? Especially if you get to multifamily. So it's kind of supplier cooling's been done. There's been the odd project in BC where they've boosted the ventilation, or like they double the flow rate or more into the suite so that you get more capacity as well. That's an interesting strategy. And again, for a short period of the year, that might be okay, right? Or heat waves or something. But there's an energy penalty. So to use that as a consistent strategy, that may not be the most efficient way of doing it. So this is like, okay, well, how do we keep to what we're already doing with ventilation air? The only way of doing that is to just increase this delta T on the supplier, get it really cold.
Super cooling.
Super cooling, yeah.
Yeah,
Super cooling.
cool. Thanks for that.
We might have one more question from John again. John, is that one's new, right?
Yes. I was wondering if you could comment on the ideal location of the return duct. What issues arise if the return duct is located in another room?
So the return duct, essentially for this strategy, the return duct is essentially the duct that's going to bring the air back to the ERV or HRV and then exhaust it. So there's actually no recirculation of air in this strategy. And that return duct is usually like the vents, the return vents are in bathrooms, kitchens, utility rooms, things like that. And as long as you have sufficient transfer area between the supply rooms and the return rooms, which are typically like door undercuts or transfer grills, as long as you provision those, that kind of thing, then it's having it in separate rooms is fine.
Oh, great. Thank you for your presentation. This was really very helpful. Thank you.
You're welcome. Thank you.
Hey, Andrew, if I can just chime in there, we just finished a project, and of course the clients wanted to have, quieter rooms because one was an office next to a kitchen. And again, a bit of a pricey solution between rooms is a product called the Van Air door, where it's got slots in the doorway, so you can have a real nice quiet space, but you can get the airflow to get that exhaust. And so, again, just fascinating to see, research talking about, these higher levels of comfort that we're trying to achieve, quiet between spaces, and seeing the technology. So again, today's presentation just is taking another level in our innovation curve in Passive House, and just that, try to fine tune the comfort equations that we're trying to go to. And so, really fascinating when we deal with the mechanicals. I have to say too, this year I've been really trying to focus on the mechanical process of Passive House, and going down some crazy rabbit holes, and then went down another one with you today. So big thank you.
Yeah, Andrew, I really applaud the process that you've gone through, not only educating yourself, but now questioning that education, pushing that education even further, and sharing it with everybody here. I know there are some students on the call, so if you have any words of inspiration for them, that would be highly appreciated. And while you're thinking of that, I have a question about the duct materials, because you did have it was an XPS version, right?
XPS was the diffuser we made of insulation
Diffuser,
was
yes,
made
I
of
said
XPS.
duct. I
Yeah.
meant diffuser, sorry.
Yeah, no problem.
Yeah, what do you think about materials? Are you seeing the materials for ducts or diffusers changing? I know you mentioned the fabric ones as well. As we're always pushing towards better materials, are you seeing any innovation there?
Not kind of in what's generally applied in Passive House. Some might still use more conventional, some might use ones that are maybe a bit more geared towards Passive House. I don't like, so no, that's part of what we scan the market, because like what's out there, who's doing what, like, is anyone doing, because cold air distribution has been around for a while. Okay, does anyone actually have diffusers that are suitable for this strategy, right?
Exactly.
And some claim, but again, it's more in the commercial industrial sector. Does that transfer over to residential? That was a big question, right? And many of them, yeah, they don't really, right? Which was it surprising? I don't know. It was like, let's find out. You can make your estimations, but yeah, until you throw it in a lab and test it out, you don't know for sure.
Yeah, I think you've just opened up a whole new world for product designers, because you've created a need that we need to fill. Well, do we have any more questions out there? I don't think we do. Well, thanks, Andrew, for joining us. We are eternally grateful. We will keep following this. And Sean wants to see it live in Canada for PH Canada next. And Kevin, Sean, any parting words?
No, great presentation, and keep pushing the envelope, and let's get better duct insulation products and duct sealing products out there. I think it's all possible. It's done throughout the world, and great people. Research labs need to take on these tests, and maybe it's some major universities really get involved. But it's exposing a void in what could be a truly optimized zero energy building. So it's cool. And multifamily is the way that we solve some of the housing problems that we have throughout the world. So it's fun to see. I love the idea of taking over like a floor pre-construction, turning into a testing lab. I could reach out to one of the projects I'm working on if you're interested on seeing how that is, but it's not going to be the same design. But it's a cool process. I always love in-suite, on-site testing the product before you roll it out. It's a great system. So
well, we're fortunate. I mean, one of the projects is a retrofit. And so we're going to be doing early stage kind of mock up in the building. It's a single family home that's being converted to a 3-unit. It wasn't intended to apply this solution, but it was kind of its own research project, and we kind of brought the two together. So we're gonna because, and actually I own the property, so I have the flexibility to do some stuff and try it. And we're gonna get an ERV in there and install some of this ducting. So because we're doing that still not in a lab, like we're working with the local college to do some of this duct testing, but ultimately we want to bring it into the home and like, okay, let's distribute it around the home and see what we're getting, right? So that's another exciting thing that's going to be coming. And actually, I forgot to mention a shout out to Swegon for their support. They lent us an ERV, one of their new CASA units for the testing we did in initial testing in refrigerator warehouse, and also Veta windows that we helped supply some components for that testing as well. So I meant to mention that, and but I remembered. So
wonderful. Yes, I totally thank the folks helping you move forward by sharing their products with your experiments, and we all have a vested interest in following these projects as you keep testing. So have a great day, Andrew. Have a great day, everyone. Thanks for joining us, and we will see you next Wednesday.